Okay. Morning. Welcome to this talk on making wind farms great again. Kidding. So I'm going to talk about why you should care about edge computing. I'm Glenn. You can reach me here, either on email or Twitter. Please reach out, if nothing else, just to say hi. Tell me I suck. Tell me I was great. Tell me that you had a good time, had a bad time, whatever. Anything that can help me improve or just meet more people. If you don't want to talk tech or tell me how I've improved, you can talk to me about my kids. I got 5 of them. The only way you can get them in one place is to throw candy at them. But anyways, we're here to talk about edge computing. Just to level set or set some expectations here. I've been diving into edge computing for a while, and I find it interesting for a whole bunch of a whole class of problems. So I'm going to talk about some scenarios where I think that edge computing makes a lot of sense, has values to offer. I'm going to talk about some dangers and pitfalls that you might run into when you decide to do something with edge computing. I'm not going to be super technical. I'm not going to show you this is how you code, this is how you do it. This is a what and why, not a how talk. So if you come here to see me live code stuff, you're going to be sorely disappointed. So just so we are on the same page here. We can defragment this room if you want to come further up. So there's lots of space over here. So what is edge computing? This is how you know this is a real talk with serious business, because I've got the Gartner hype cycle. And first of all, edge computing is hyped. It is right up there on the top of the what's coming. Who knows what the Gartner hype cycle actually is? 0, 2, 3. So the hype cycle is, Gartner is an agency that do a lot of predictions and analysis in our industry. And they have the hype cycle, which shows the sort of the maturity of different things. They start off here in the innovation trigger phase, where it's a great concept, moves into some early success stories, maybe a lot of failures, lots of expectations, and the peak of inflated expectations point. Go down to the throe of disillusionment, where people have done a lot of weird stuff, and a lot of people fail to deliver, and everyone's like, nah, never gonna work. And then they come into slope of enlightenment, where like, okay, maybe we got this, maybe we're finding a way to do this together. And then you come into the plateau of productivity, where things just start working. And basically mainstream. They also have some predictions on how long it's going to be before they go here. They estimate this will be 2 to 5 years before edge computing is a mainstream thing. So for now, we're all the way on the top here, almost crossing over the crest here. So that means there's a lot of people talking about it, present company included. But there haven't been enough done to create the bunch of success stories you might want for everybody to go, yeah, okay, that's it. Its market is slightly mature. There's different players, different offerings, maybe not talking to each other as much. But at the same time, people are optimistic. Last March, a company called Futurum surveyed 500 businesses in the US, ranging from about 500 to 50,000 employees. And they surveyed them about edge computing in their Edge Computing Index. And 76% of those companies said they either are or will be investing in edge computing in the coming 6 months. 93% said they would do it within the year, 12 months. 5.5%-ish said we're going to do it within 24 months. And 1.6% said that we have no plans. So this was a work week. This will be the 2 last hours on Friday, and this will be the last 40 minutes on a Friday. The rest think, yes, okay, we're going to do something about that. Now, the index says nothing about how much they're investing, just that they are. They have plans. So a lot of companies are looking at this and saying, okay, we got to look into this. We got to make some investments to figure out if this is right for our business. Now, who has heard of the Internet of Things? Great. This is a story that will be billions of devices all around the world, all of them collecting data. These red graphs are actual IoT devices, and people do connected devices. And fun fact, this number here of connected devices includes about 1.5 billion landlines, phones, for some reason. They are counted as a connected device. But it is growing. There's going to be a lot more of these. And all of these IoT devices, Internet of Things, they collect data. That is basically what they do. They collect some data, and they usually ship it off to the cloud. And people also call this the Internet of Shit. The Ring security camera that made the entire catalog of videos available to a huge group of employees who do not need access. Oops. I had to walk home because my smart bike wouldn't unlock. So there's issues with the internet. But why are they sending this stuff off to the cloud? And there's been stories about people who drove a Tesla, parked on some deserted road, went out, closed the door, Tesla locked, and they couldn't unlock it from the phone because the car didn't have internet. There's all kinds of stupid stuff like that. Because they're all suddenly dependent on the cloud. And why do they do it? Well, mostly because it's cheaper and easier for the developers than to set up a whole ingress infrastructure in your own data center, which, by the way, is forecast to be shut down. In about 5 or 6 years, about 80% of the data centers will be shut down and moved to the cloud. So people have stopped having their own servers in their own basement and just rent it somewhere. So we're not going to escape the cloud. It makes good sense to use the cloud to collect data and manage our IoT devices. And also because in the cloud with the large cloud players, they have specialized services to manage our IoT devices. So in many cases, you can, and you probably should, consider, do I actually have to do this in the cloud? Can I take my compute or storage, my compute and my decision making, and can I move this onto the device? And that is the definition of edge computing. I'm taking computing power, storage power, and decision-making power from the cloud and shifting it on to the actual device, deployed in some remote location maybe. And of course, wanting to keep the height factor up, people have started referring to this as smart devices. So that's another name you find for it. I used to think that was a pretty low bar for calling something smart. But then I looked at politics and I figured the bar wasn't that low anyway. So, what does an edge device look like? These are two edge devices. This one is a microcontroller. The actual device is this chip here in the middle. The rest is just make it easier for you to develop on it. If you're making a bunch of devices, you take just that and solder onto your own hardware. A microcontroller is a small and relatively low-powered device, often what's called a system on a chip, that can have some program, read a bunch of data from external inputs. Most of the other stuff here is just power management. And doesn't have a lot of compute power, it doesn't have a lot of decision-making power out of the box. You also have these kinds of devices, which is basically a PC, but often a more ruggedized context. This could also be a Raspberry Pi if you want to play around with this stuff. But if you're doing something professional, you'll usually buy one of these more industrial devices. Can be mounted on DIN rails. Usually an x86 processor of some kind. It's called an application CPU, often an Atom. They're low-powered compared to my computer, but they're significantly more powered than a microcontroller. On these machines, we can run a lot of code. We can run decision making, we can hook up storage, and we can do all kinds of weird and wonderful shit. In many cases, these microcontrollers act as inputs to these. So we'll have microcontrollers doing measurements on machinery, environment, all kinds of stuff, just ingressing data and feeding it in to a larger, more powerful device, which can run more stuff on it. So I'm going to talk a little bit about some use cases and some scenarios where processing data on the device and making decisions on the device before you start sending stuff to the cloud makes a lot of sense, to me at least. So what is life like on the edge? What are some reasons why you could be here? Privacy. Maybe I don't want my stuff in the cloud. For instance, there are numerous cases where data have been uploaded to a cloud and then exposed. There are, if you follow people on Twitter, like Troy Hunt or Scott Helm, they'll often reveal security mistakes, to put it nicely. You'll have cases where people can go online and see other people's babies in their baby cams. There's been cases where people have taken over baby cams and started sending voice out through the baby cam, which is really creepy when someone else is talking to your baby while you're not there. And also the fact that, for instance, you have doorbells with cameras in them that will tell you who's at the door. So your doorbell can send you a message that so-and-so is at the door. And you can get input, and maybe not people you know, but it can also do people you don't know. Amazon has a patent going where they will try to identify suspicious people. And the patent goes on to describe how different doorbells in the neighborhood will work together to try to identify people acting suspiciously and proactively notify law enforcement. So your doorbell is going to call the cops on people roaming your neighborhood. Which sounds like a nice idea, but I don't really want my kids' faces going up to the Google Cloud or Amazon Cloud every single day when they come home. I don't want the comings of goings from people from my house be uploaded somewhere. I mean, people are starting to get a lot skeptical to the data Google collects on you when you surf the web or Facebook or anything like that. It's like, yeah, I'm going to upload everyone who goes into my door, who they are, what time they come. I don't know. So what we can have here is that you could have on that device, you could have an image recognition, facial recognition module running on the device that could be trained with images from your family. And it would be able to do image recognition or facial recognition without any data leaving the actual device. It could even be blocked from leaving the device. There would be no option for the data to escape the device because it wouldn't be enabled. And then you can send me messages for the exact things that I would like you to send me messages of, like there's an unknown person standing outside your door. He's been standing there for 5 minutes. I should be concerned. Another case, it was a pizza chain in Oslo that put up one of those digital signs, you know, those monitors that people just flip on their side, and they show ads. And you couldn't tell just by walking by, but there was a wooden frame, it looked really nice, and above it was a little black hole with a camera in it. And it would do facial identification of people in front of the sign. And it would identify whether you were it would put you in an age group, like young adult, and it would identify your gender, young adult male, and it would track if you were paying attention to the actual ad. And it would measure how long you were paying attention. And they used this for segmenting different ads, because they wanted to know, OK, do these ads work better on this segment? In this particular case, if you were a woman, you were shown ads for healthy alternatives. You got salads and stuff. If you were a man, or it identified you as a man, it would show you ads that contain more meat. And they were measuring, say, do people respond differently to these? Do we get more attention span on this? And this was revealed because the signage program crashed, and the software doing the image recognition was left on the monitor. And this one guy goes back and goes, what? So he took a picture of that, put on Imager. So here you have male adult, attention time 0 out of 297. Male young adult, attention time 406 out of 406. 93 out of 593. And it would do stuff like whether you were smiling or if you had glasses and stuff. This is creepy. This is, personally, I think the morals are murky here at best. And the legality of it is in a gray area, because you're not technically doing video surveillance because they never stored anything. They didn't store the images. The images were processed in memory, metadata extracted, and then the image data disappeared. And it only saved metadata. So we're like, oh, we're fine, this is metadata. The legality is murky. But it was a somewhat mitigating factor. Now, this would have been better if they put up a sign like, OK, you're being tracked. And we can still be creepy even if we're doing local processing. So another less nefarious case, I would like to have software control the heating and electrical power usage in my home. I'd like that. I would like to have software that would learn my usage patterns of my house, that knows when I'm home, when I'm not, who's home, how many people are home, what rooms we use, and adjust the heating and all of that so that I'm comfortable and pay less. As we move forward, we get solar panels and house batteries, and it can help make intelligent decisions on shifting power from these devices. So instead of getting spikes and paying a lot of money in overcharge, I can get a flat consumption of my power. Now, this exists today, and it makes sure, if you do that, all your data is in someone's cloud, where they have complete knowledge of your usage of your own home. I'm uncomfortable with that. And frankly, so should you be. But this is not a huge issue, because we can put this intelligence in a local device. We can run machine learning models on devices. I'll come back to that. So the analysis engine can go in a locally installed device, not accessible from the outside, and it will report unidentifiable metadata, because I'd like to know how much money I'm saving, which is nice. So the device can pull down prices. I can pull stuff into my house instead of pushing it out of my house. So I can go online, and it can push you have saved this amount of money today. And I can go online and see how much money I've saved, which is fine. Healthcare is one. So a project I was involved with some people, they were making a device with a camera that could identify if a person was laying down or not, which is useful in hospitals to see if people are in their beds, or if they're out of their beds, or if they've fallen down on the floor. It's useful in old people homes, where they are not, I don't know what the English term is, but you have like houses where old people are mostly by themselves, but they get some help every now and again. And sometimes they'll fall, they'll break a hip, and if they don't have their alarm on them, they're stuck there. And the privacy concerns of sending a live video feed of someone's house to some device somewhere to monitor this is a real concern. It should not be taken lightly. Again, you can have devices that do this analysis locally on the device. So privacy is a big thing about it. It can solve a bunch of privacy concerns. Another problem is latency that it can solve. I was also told that this is also how you tell it's a good presentation if you have the wow dog. I blame her. So say you have a machine that has a bunch of sensors that can inform you how this machine is working. And it reports this up to the cloud, and we can do preventive maintenance. We can see, OK, this machine is about to fail. And some machines, if they fail critically. And you might have a short amount of time to detect that and stop the machine. So there's a company in Sweden called Sandvik, which has a lot of metal grinders, metal CNC machines. And they had this operation where they had sensors that monitored a bunch of different things. They had 900 moving parts of those machines, and it sent all this data up to the cloud. And they could detect a failure condition and send an alarm down to stop the machine. That took 2 seconds. And they switched to putting that logic into the device instead. And they went down to 100 milliseconds. So it's a 20 times improvement, which was enough for them to stop the machines before they failed catastrophically and save them tons of money. Literally tons, if you put it in bills. So what you would have then is you would have stream analytics. Stream analytics are different from just measuring a value and seeing, is this value within some parameters? Stream analytics will measure values over time and look at changes over time. Has this value changed with so-and-so in the last 5 minutes or in the last 10 seconds? They can measure a value every single millisecond, but the last value is not really interesting. It's a few values back. And so these stream analytics engines can also be deployed to these devices. Now, the fun part that Sandvik's discovered was that they could use the same programming model in the cloud as on the device. I'll get back to that as well. So latency can also be effective when it comes to user experience. Voice recognition, for instance. It takes a couple of seconds to get it up to the cloud, stream your voice data up to the cloud, audio, translate it there, get into text, make an action, send it back again. It would be a better experience if your device could translate your audio to text and just transmit a short amount of text up and get an action back. So latency can also help with the user experience and not just being fast at fixing something. We can be resistant to failure. So like the Tesla car that didn't work when it didn't have internet, you couldn't literally not open the car on a remote highway in Nebraska somewhere. Being resistant to intermittent failure, because if you depend on the cloud, that's a dependency that you have no control over, and there's lots of different variables between you and that dependency. You're not just dependent on the cloud, you're dependent on the Wi-Fi, you're dependent on the ISP, you're dependent on the guy across the street that's digging the hole and not tearing up your fiber. So in my house, if I have managed heating, if the cloud becomes unreliable or becomes unavailable, what happens to my house? The logic is no longer able to control my house. And that, how many customers needs a bad experience before that has a PR value for your company in the negative sense? I was in a meeting with a utility company once, and there was a guy there, and he was really on the edge in the smart home thing. He bought a lot of stuff. Nothing was standard. He put a lot of stuff together, managed a whole bunch of things that pulled a lot of electricity. And one time he comes home and all of his stuff is in a pile on the living room table. Because his wife had come home from her workout and had to have a cold shower. Because his system turned off the water heater to save money and didn't turn it on again. So while I do subscribe to the slightly amused wife, happy life, slightly annoyed wife, amusing life, the theory, the angry wife is not a good, happy life. So make sure your stuff doesn't make customers angry when something else fails. Making sure that doesn't happen is a feature of your software. Having a device that can keep processing input, keep giving useful output, even if the cloud is gone, that is a valuable thing. Another issue that edge computing can solve is size. The sheer volume of data being ingested can make it impractical to ship this to the cloud. The canonical example everyone pulls up is the autonomous car, which will generate about 300 terabytes of data a year. That's like 35 gigabytes of data each hour. And it's going to grow. I was at a client recently where we've been building a system that, I can't talk about the actual system, but it generates about 3 gigabytes of data per second. It totals out about 300 terabytes a day of generated data. And this data needs to be analyzed in real time. And we have not only analyzed, but we have to do fast Fourier transforms on it, on a GPU rig as well. And we have to look for certain patterns and certain things that will indicate something is wrong. And the things that can go wrong are in the million-dollar class wrong. So there we basically have to build a rig that has a whole bunch of storage, huge amounts, in the petabyte range, like thousands of terabytes, to store this data, because we want to go back every now and again and say, okay, we had an incident somewhere, let's go back and look at the data for that period. We're not going to store it internally, but we're going to store a few weeks of data. And we looked at just putting this in the cloud. It involved putting a 100 gigabyte internet connection out into the North Sea, which was inconvenient at best, but it was possible. And it also turned out that the cost of ingressing this into the cloud and storing it in the cloud was enormous. So putting up a small cluster of machines, well, small as in 16 or so machines, with a massive amount of storage, ingesting 15 different data streams, totaling out at 3 gigabytes, bytes, not bits, bytes, per second, was a lot cheaper. Now, this is not one of those little Atom C processors you just put in your DIN rail thing. This is a massive rig. It's like a rack. But it's still edge computing. So that we can analyze the data coming in. We have a bunch of GPUs that will do Fourier transforms on it, translate data, look for anomalies, and alert someone says, here's something weird. You should look at this. Another problem with devices, especially if you have a lot of devices, is that the bandwidth cost becomes significant. Because not every IoT device has a wired connection or a Wi-Fi. They rely on mobile network. And it's not much if you have like one device, but if you have like thousands of them, it adds up fast. So we'd like to keep that data, the data traffic low, instead of sending all the data. And if you measure often, that can become a lot of data, and just send aggregates or anomalies. Like instead, maybe we measure every second, but we'll send data every 15 minutes. Here's what happened in the last 15 minutes. That can give you significant savings. From going to once every second to once every hour is a savings of 3,600 times of data. Also, interconnected devices, this is the last one. Things that are connected together. This sort of builds on the previous, where you have devices with little or no or slow connectivity. So instead of having all these devices send data in and something else deciding on the whole picture, you can have devices talk to each other through a mesh network, a radio network, basically, which is free. It's just very short range. But one can talk to one, they can pass it on to another, and they can talk to each other like that. And they can use that to make decisions. There's a company called Swim.ai who have built a system that does this with traffic lights. So traffic lights have sensors so they can know how much traffic it is, how many pedestrians do we have here, and so on. And can make decisions based on a system as a whole to keep the traffic flowing as best as possible. With machine learning algorithms or models running on these devices, saying, OK, in this situation, we should probably keep these lights green a little bit longer to get that going. We haven't really built up here yet, and so on and so forth. And of course, they aggregate all this data up, and whoever is in charge of traffic flow gets a nice little view and see exactly what's happening. But the bandwidth costs are low because it's aggregated data, and decisions are made locally. So these are some scenarios that I think make sense for using edge computing, to put data and logic on devices. Now for the problems. Dangers and pitfalls. Of course, security is still a problem. Notice I didn't say we solved security. We moved security somewhere else. That can make it easier in some cases. It's easier for me to be secure that my data is safe on a device hanging on the wall in my house than in some data center somewhere. If someone wants to get at the data of how I'm using my house, they have to break into my house and steal the box on my wall. It would be a lot easier just to sit outside my house for a week. So the threat model is not really applicable anymore. But when you're spreading your cloud out like this, you're also spreading out your attack surface. So instead of having relatively dumb transmitters just sending data up, you'll have small computers not only transmitting data up, but also receiving data back in, doing compute, doing intensive things, and they are open for attack. There was a case a couple of years ago where a botnet infected fridges, refrigerators in your kitchen. Because they had a little computer, had a little monitor on it. It can tell you how much milk you had, or can send you photos of whatever was inside your fridge. Because that's apparently a huge problem for people to know what they have in their fridge. So we have to make $1,000 fridges with cameras in them. And so they were infected, and they started sending out spam emails from the fridges. So now your fridge didn't only know how much milk you had left, it also had a great deal on penis enlargements. Now, so compounding on this risk, many IoT devices are not really designed with security in mind. They are often systems that are put together by people who do not think about security first. They are often meant to be inside different houses or buildings. And when you start adding stuff to it, maybe it doesn't work as well. And they might not be in a secure and controlled location, because the traffic lights are not really a secure and controlled location. People will try to tamper with this. So how can you make your devices tamper-proof? How can you make sure that secrets and data you put into this doesn't come out of it? What happens if a device is actually tampered with? How do you handle that? Do you have to go out and stuff like that? So there's considerations to make here. Now, there are some people who try to make this better for you. Azure Sphere is one of them. Azure Sphere is a trifecta of a secured MCU, microcontroller unit, which is one of those little systems on chip. So it contains custom silicon in it for security-specific purposes. It can work both as a real-time processor and also an application processor to actually run code on it. The Azure Sphere OS is Microsoft's first released Linux version, which is a specially custom Linux variant of a real-time OS, which makes timing of your code deterministic. Instead of having to wait 5 seconds for garbage collection, you can determine it beforehand that I will have code running at these intervals. And then you have the Azure Sphere Security Service, which is a cloud service to help broker trust for device-to-device communication, device-to-cloud communication, device-to-service communication, detecting threats, upgrading firmware, all kind of that stuff. And these things together come in this little package. This is one of the first kits you could buy. So you get over-the-air updates. You get built-in capabilities for talking to the Azure IoT Hub, which is a service to ingest data from IoT. You can talk to all kinds of HTTP servers. You can talk to other cloud vendors through this device. They're pretty open, actually, on it. So I'm guessing that they're just betting on people taking the easy way out and just go with Azure all the way. AWS has something called the Amazon Free RTOS, real-time operating system. It's a version of the Free RTOS kernel that they have extended with services for security, talking to the Amazon IoT service, functionality of connecting to other local devices, remote updates, all kinds of stuff. Unlike the Azure Sphere, it doesn't come with hardware, but they have several pre-qualified devices, including the popular ESP32, which is a tiny little chip that does a lot of nice little stuff with Bluetooth and Wi-Fi, all kinds of stuff. Very handy for the hobbyist IoT hacker. And you can remotely manage it from the AWS IoT service, over-the-air updates, all kinds of that. Also, physical security is a thing. Not only the devices, but whatever code you put on it has to have some kind of measure of security. Do not trust user input, and so on and so forth. Also, things are maintenance. What is the lifespan of devices you're putting out there? When do they have to be changed? What happens if they break down? When you're putting physical stuff in the physical world, you have to start thinking about physical things. How do we update this? The most common thing is to go for over-the-air updates. And that sounds like the obvious thing. Like, why would someone not do that? And I know people who have deployed 60,000 devices without the ability to do over-the-air updates. And then they came and they were, it'll be fine. Don't worry about it. It's a simple thing. It's a thermostat thing. Don't worry. And then something changed and like, yeah, we have to update the firmware. Which involves a person with a laptop going out, unscrewing something in the wall, plugging in a cable, pressing a button. Okay, I'm done. Screwing it back in again, driving to the next house. So things often work a little bit differently in the embedded world. But don't do edge computing unless you have a specific problem you want to solve. Edge computing is a specialized approach for solving specialized problems. Enterprises are often guilty of adopting a technology just because it's mentioned more than once in some kind of press, or they heard a talk on it somewhere on some random conference. It's like, oh, that sounds awesome. But in doing that, it will cost you money and it will add risk. Edge computing definitely falls into this category. If you decide to go for edge computing, it will increase your risk and it will cost you money. It's not a general purpose approach to computing, which cloud computing is. It's cloud computing is what we call a macro pattern. It's a pattern that works on a wide area of problems. Includes a great deal of other technologies. Edge computing is what's called a micro pattern, addressing a small subset of your needs. The problems are specific, and you have to be tactical around addressing those specific issues. Now, a little bit more about how we can do this. Azure Cognitive Services. Anyone heard of Azure Cognitive Services? Okay, cool. Azure Cognitive Services is, or Microsoft Cognitive Services, is a set of pre-built machine learning models that will do things like face identification. It will give you a picture. It will tell you where in the picture different faces are. It will tell you the approximate age, gender, emotion. You will get a number if they are angry, curious, sad, happy. It will give you points in the face. The eyes are here, the mouth is here, the top of the lips are here, the body. It's amazing what they can get out of this. You can send it images saying, this is a boat, this is a, anyone use PowerPoint, the latest version? If you insert a picture, it will come up with an alternative text automatically saying, looks like so-and-so. So you can have your own image facial recognition service. You can feed it a bunch of faces. And then you can say, give it another image of face. Do you know this, recognize this person? And we'll go, this is this person here. You told me about this one before. It also has some half-baked. So all of these a few of these services are now available as containers. So instead of running them in the cloud, you can take that service as a container with a little web front end on it, or not a front end, a little web interface on it, an API, and you can run that on a local device. They have some half-baked services, like Custom Vision, which doesn't recognize anything, but then you feed it a bunch of images and tell it what these images are. I tested this once because someone was talking about a thing, like, that's going to be hard to tell the difference between everything. It's like, nah, it's not. So I taught it to tell the difference between a plug in the wall and a light switch. Found 10, 15 images of each, loaded them up, says this is a plug, this is a wall switch. After that, I could feed it an image, it would tell me, that's a plug, that's a wall switch. And then I discovered I hadn't trained it with plugs in the wall with an actual wire in them. So I uploaded 4 or 5 new pictures of that, and it was good. So you can do this with all kinds of stuff that is custom to you. And what you can do there, you can generate that machine learning model as a file that you can deploy on iOS, on Android, or in container, and run it locally. It is super easy. And you also have the Azure Machine Learning Service, where you can take your own machine learning code, make your own Python code, train it on the massive GPUs they have in the cloud, because that's what machine learning does. You take some code and you train it on a massive set of data. That is the resource-intensive part. What you get out of it is a bunch of values that is actually pretty small and compact that you can take with you and deploy on low-powered devices. Azure IoT Edge. It is a service and a concept from Microsoft where you have, in Azure, you have features like Azure Functions. Anyone used Azure Functions? Pretty nifty. Just write some code. Here's what comes in. Write some code. This comes out. I'm done. You have Stream Analytics in Azure, which will take a data stream. You can do what's called temporal queries, the queries over time. Give me the value, the change of this value for the past 5 minutes. With IoT Edge, you can take those same things and deploy them down to a device. What IoT Edge does is when you register a device as an IoT Edge device, you install the IoT Edge client, which has 2 parts. It has the agent and the hub. The agent is responsible for checking a cloud configuration which says you should install these containers. The Azure function comes down to the container. The stream analytics come down to the container. You can run machine learning models as container. You can build your own containers with your own code. This can run on anything from a Raspberry Pi and up, basically, and even some custom devices, as long as it's ARM or x86. The agent will pull down these, and it is also a configuration saying that how the data from one container, where should that go? And you can hook it by configuration to different containers or up to the cloud. So you can define in the cloud saying, I will have my own custom code that reads. One example I did, we had some house batteries in a smart home that had the worst HTTP API I have ever seen. And if you want to, I'll hook up with me after my talk, and I'll gladly tell you how much that sucked. So we made a little container that would read that API, feed that data into the cloud. It was a simple thing. Or we could feed it into a stream analytics and do analytics on the battery usage over time. And those are just configuration changes. What I have is, I have a little container, read some data, put some data out. The hub gets a configuration saying, where should that data go? Should I feed it into another container? Should I just feed it up to the cloud? And so it becomes a configuration problem. I can create a configuration. I can push that configuration to thousands of devices at the same time. And they will automatically update this. They will pull down the Docker images, restart the images, and we'll just keep going. So as long as you can run Docker on the device, you're good. Advantages here, you get some good service out of the box. You can just configure those up. They work exactly the same as their cloud counterparts. And you get a bunch of infrastructure out of the box. If you want to update the function, update the stream analytics code, update your own thing, create a new one, push it to your Docker registry or your private container registry. It will pull it. It will show it up. Makes it really easy. AWS has something called Greengrass, which is a similar service. It has the Greengrass core, which runs on an ARM or an x86 device, so bigger than a microcontroller, but it supports running AWS Lambda functions locally. And it has some service of messaging and stuff. And this has a nifty little thing. Remember the Amazon Free RTOS thing? So if you have those devices, those small microcontrollers, as sensors, if they are connected to the same network as a Greengrass core device, they would automatically detect each other and hook them up. So you basically configure your thing in the cloud and saying, here's my Greengrass core. And you create a little neighborhood or a group, Greengrass group, saying, to this, you should connect this device and this device and this device. And it will just go, OK. And it hooks up. And you can do functions, ingesting data. You can store it. You can cache it. If the cloud goes away, then it will cache your data locally before shipping it up. You can run AWS SageMaker machine learning models on this device. So a nifty little thing. So look into that. And if you want to get started with edge computing, look into the Greengrass or the IoT Edge, depending on which cloud you prefer. They're easy to get started with. You can run them on your computer as well. They have emulators or clients for a normal PC, so you don't need any hardware to get started with unless you want to. AWS has this one little thing as well. This is the Snowball, which is a little computer that you can order, and it comes like this. It doesn't come as a shipping container. It is the shipping container. It has a little e-ink monitor on it that will show the shipping label when it's being shipped. And on this one, you can run EC2 instances, which is the Amazon virtual machine thing. You can also run AWS Lambda functions. And it has a bunch of disks in it. The initial version will give you 24 virtual CPUs and about 100 terabytes of disk space. And you can use it to ingest data in a super remote location, on a submarine if you want it, or whatever. It's pretty ruggedized. They test it by putting it on a barge and then blowing up explosives in the water underneath it for shock testing. It is absolutely insane. You can cluster them together to have petabytes of storage spread out over these things. And you can get versions with GPUs in them as well for machine learning stuff. And then when they're full or they come back from wherever they were, you pick them up, you press some buttons, shipping label comes up, and you just ship them back to Amazon, and they'll take the data and dump them in your S3 storage. They also have, I don't have a picture of that, but they have the Snowmobile, which is a 42-foot container coming on a trailer with a truck with storage. And you just plug it into your network, and you fill it up with storage, and they drive it back to Amazon, which is a pretty cool service. And also, we have some specialized chips. Who here has a phone with an AI chip in it? If you have one of the latest Huawei's, the P20s, you do. If you have the Google Nexus 3, I think it is, you have an AI chip in your phone. My camera, if I point my camera at something, it will detect what I'm pointing it at and choose the appropriate mode for my camera. It's like, oh, you're taking a portrait because I can see a face. It takes amazing pictures at night because it uses machine learning to put a lot of pictures on top of each other and see which parts change and do a whole lot of magic. But they're also making even more specialized chips. So this little thing here is a Google Tensorflow machine. And now not only can you have machine learning models running on your thing, you can start training models on small devices. So not only can you make a model, pre-bake it, put it on device, and because when you made the model, it is made. It doesn't change necessarily. But with these kinds of chips, you can train your model as you go along, which becomes a really, really powerful thing. So you can also move the training work down to your machine, so you don't have to upload images of your family to start training. You can actually literally feed them to the actual device. This one is cute. Anyone know what this is? This is the Azure Kinect camera. It is a 3D camera that generates, basically, put it simplified a bit, it generates point cloud in 3D of what it sees. And it is about this big. You can use this. This is the 4th generation of the Kinect. The first one was an Xbox 360. The second one was an Xbox One. The third one was an HoloLens. This is the 4th generation of the Kinect camera. And if you've seen some of the demos on it, it is astonishing. Has anyone ever used a HoloLens? When you put something on the wall, did you feel that it was steady on the wall? It didn't like flitter and at least my experience, it is dead steady. You put it somewhere and it just stuck. You try this stuff with your phones and stuff, and they'll shake a little bit and they'll go a little bit with that. And it's okay, but when you put it with the HoloLens, it is there. No matter how you move your head, they are stuck in 3D space. These things will help you do the same thing. So you can make devices that will see in 3D what is happening. For instance, healthcare. Are people laying down or not? Because suddenly becomes pretty easy. So one last thing before we round off. Fog computing. Has anyone heard that term? Cisco coined it years ago because they wanted to be relevant. Because they didn't do cloud very well, and people started not caring about the network as much as they did before. So Cisco came up with something called fog computing, which is connected to edge computing. So here's the edge computing devices. And on top, we have the cloud. And in between the cloud and the edge, we have the fog, which are basically aggregating devices on different levels. So you can have stuff in your house, and then you can aggregate this data on devices in your building, in your neighborhood, and whatever you go up. It is a whole bunch of, there's 2 organizations. The name is it the Open Fog Consortium, which sounds really weird. And there's something called the EdgeX, which are now starting to work with standardizing how should these devices talk to each other. How can we make this interchangeable and not full vendor lock-in, whatever you do? So there's things happening here in this space to make sure we get over that peak of inflated expectations and start going down, and as soon as possible come up for the throw of disillusionment and start getting on a path of we can actually work together on this. So that was what I had. If you have any questions, you can ask him now, or you can contact me later, or you can try to find me somewhere. I'll probably be hanging out throughout here or at the party later. Any questions? Either I've been incredibly clear or incredibly obtuse. Okay, thank you. Oh. And thank you to Morten for being a volunteer. So he gets a chocolate. There you go. Give him an applause. He donates his time so you guys can have a good time. I'm done.